Hello, my name's Peter Anderson, and this is our work on sim-to-real transfer for vision and language navigation. Vision and language navigation, or VLN, is the task of following natural language navigation instructions in a photorealistic environment. Typically, this task is studied in a graph-based simulator in which the agent receives an instruction, such as the one shown here, and then tries to navigate along edges in the graph to arrive at the correct goal location in a previously unseen test environment. In this work, our goal is to transfer a VLN agent trained in simulation in this way to a physical robot, in this case a turtlebot, to see if progress in VLN can be parlayed into progress in robotics. Our evaluation environment, called CODA, consists of a 325 square meter office space shown here in floor plan view, which we digitize and annotate with 111 English navigation instructions comprising 1.3 kilometers of language-guided trajectories. This gives us parallel sim and real versions of a previously unseen test environment. Our hope is that we can achieve similar instruction following performance in the real world as the sim. So in the simulator, at each time step, the VLN agent takes as input a panoramic image of the environment and a set of action candidates defined as adjacent nodes in the navigation graph. The agent then selects an action, and the simulator teleports the agent to its new pose, usually about 2 meters away. To support this same agent on a turtlebot, we first equip the robot with a consumer-grade 360-degree Ricoh theta camera to provide the visual input, and we then propose a subgoal model to predict nearby waypoints or subgoals that can be provided to the agent as action candidates in lieu of the navigation graph. Finally, to navigate to the selected waypoint, we use standard ROS-based SLAM and path planning modules. Looking into the subgoal model in more detail, it's comprised of a pre-trained CNN and a UNet. It takes as input a 270-degree laser scan, plus the 360-degree image at the current location. And like the VLN agent, it's trained on the room-to-room dataset based on Matterport 3D, in this case to minimize the sinkhorn divergence between predicted subgoals and the actual adjacent nodes in the navigation graph. One further issue we find is that compared to the high dynamic range Matterport camera images used in the sim, the cheaper robot camera has substantial visual domain differences, and our test environment is also significantly affected by variations in lighting conditions as illustrated here. To address this, we use an approach similar to domain randomization, in which we apply random color jitter to the visual inputs while training both the VLN agent and the subgoal model. So turning now to results, in the sim version of CODA, the agent achieves close to 56% success at reaching the navigation goals, which drops by about 6% when we substitute imagery from the robot's camera, although our domain randomization strategy claws back around half of that. On the robot, we consider two settings, with and without a pre-built map, which consists of an occupancy grid and a navigation graph, but no semantic labels of any kind. Here we can see that when this map is available, performance on the robot is actually quite similar to the simulator. To look at an example navigation, on the right-hand side we can see the occupancy grid and also in blue dots the navigation graph that is provided to the robot. At the top right there's an external third-person camera view illustrating the progress of the robot, as it follows the instruction that is illustrated at the bottom of the screen. Go between the table bookcase and the sectional sofa on this floor. Finally, on the left-hand side, we see the two camera images coming from on board the robot. The bottom image is the panoramic image that's used by the VLN agent. And so in this case, the robot's actually successful at reaching the goal. The final setting is without a map, and here we see that the success rate drops substantially from around 47% with the map to less than half of that. And so in this setting, Let's have a look at an illustrative example. On the right-hand side, we see that at the beginning of every episode, the robot has no information and is basically performing SLAM from scratch to build an occupancy grid, while at the same time, the subgoal model is attempting to predict nearby waypoints that can approximate the navigation graph. And so in this case, the subgoal model actually fails to predict waypoints that are identical to the navigation graph, and those errors cascade over time. So in this particular episode, the agent will stop before reaching the goal. So in summary, this is the first attempt to transfer a VLN agent trained on the room-to-room dataset to a physical robot in an unseen test environment. We find that the sim-to-real gap is small if a map consisting of an occupancy grid and a navigation graph can be provided. This contains no semantic labels and is actually fairly easy to collect and annotate. However, in the absence of any map at all, with the robot restarting SLAM at the beginning of each episode, the sim-to-real gap is quite large. This indicates that aligning the agent's action space in sim and real seems to be the main obstacle, and it's very promising that we find that once we control for this by providing the map, transferring the learned language groundings from the simulator to an unseen physical environment actually works quite well. Code is available at the following URL.